rates. So we'll start on page,
Oh, the projector.
oh. Okay, page 97. So related rates, they're just a particular type of, they're word problems. There's just a few sort of varieties of them. They're not very hard once you get the hang of them. Now we do them, the reason we do them right after the section on parametric functions, where we think of x and y as functions of t, third variable. Well, here you can think of, we're going to have probably at least two variables, and we're going to have their derivatives with respect to time. And we're going to use implicit differentiation, but it's going to be a little bit different because we're going to be taking the derivative of everything with respect to time. Okay, so here's an example. There's always some things that are fixed and some things that are changing. There's usually something moving or getting bigger or getting smaller. So it says here, a rocket is launched vertically and is tracked by a radar station, which is located on the ground 3 miles from the launch site. So here's the launch site here. And of course it's fixed. And the radar station is also fixed. So this distance between them, 3 miles, is also fixed. So it's important to distinguish between the things that are changing and the things that aren't changing. But this distance here, we could call this, say, x. And this distance over here, y, they're both changing. They're getting bigger, right? So the idea is to make an equation that relates your variables. In other words, an equation that contains your variables. So what equation could we make here? Of course, this is a right angle, a 90-degree angle. So what equation could we make that would be true, that contains x and y? Sorry, did you say? Are you sure? Pythagoras, right. So remember, right, Pythagoras. So remember with Pythagoras, you've got the right angle, A, B, C. And A squared plus B squared equals C squared. And remember, A and B are the legs, right? The so-called legs of the triangle, they're the ones that are next to the right angle. And C is the hypotenuse. It's the longest side, right? So it has to be over on the other side by itself. So here, which one is the hypotenuse in our triangle? Y, right. So what would our equation be? Right. Or 9 plus x squared equals y squared. So once you have your equation, now if you look at the problem here, well, it gave us that 3 miles. That's that fixed thing. That's fixed, right? But it also gives us some other distance. They want to know, what is the vertical speed of the rocket at the instant when its distance from the radar station is 5 miles? And this distance is increasing at a rate of 5,000 miles per hour. So your very first instinct is probably going to be, well, put 5 in there for y. But you don't want to do that, okay? Because you've got to set up the equation first and take the derivatives before putting constants in for your variables. Now, it's okay to put the 3 in because it's not a variable, it's fixed. So it would just be like, if suppose we had something like f of x equals x cubed plus 2x. And you wanted to find out what is x f prime of 5. Would you plug the 5 in before taking the derivative or after? After, right? Because if you plugged it in before, well, you just get a constant, and then you check the derivative, it would be 0. So that's not what you want to do. You first take derivative, second, okay, I'll maybe then plug in value for variable, right? So you'd have to take the derivative, and it's f prime equals 3x squared plus 2, and now you can plug in 5. If you tried to do it the other way, if you plugged in 5 first, and then tried to take the derivative, you just get 0, right? It wouldn't make any sense. Well, it's the same with these things. The x and the y are variables, and we're interested in their derivatives. And matter of fact, we've been told what the value of the derivative, because, okay, so we've been given this here. That's a value for y. And we've been given this here. This distance is increasing at a rate of 5,000 miles per hour. So that is a value for y prime, or dy dt. The rate y is changing with respect to time, right? So we've got to figure out how and then what we're trying to find is, there's always an unknown rate that you're trying to find. What is the vertical speed of the rocket? So that's our unknown rate. And that in this case is dx dt. So anyways, now that we've got our equation, we come along and we do d by dt of both sides. And we're doing implicit differentiation. With respect to time t. So remember before, when we were doing implicit differentiation, we were always doing d by dx. Like we might So recall the implicit differentiation we have done so far. You might have something like d by dx of x squared plus y squared equals d by dx of, I don't know, 25 or something like that. Just a sec here. Move this out of the way. And d by dx, now remember here I said the x is matched, so it's just 2x. But here, the x doesn't match the y. So that's where you have to use the chain rule, right? So it's going to be just 2x plus 2y, and you can call it dy dx, or y prime. And on the other side, you get 0. Okay, so remember that's what we've done so far. Well, this is going to be a little bit different because we're not doing d by dx, we're doing d by dt, a third variable that is neither x nor y. So the t doesn't match the x, and it doesn't match the y either. It won't ever match any of the variables. So you have to use the chain rule for for all the variables. But of course, d by dt of 9 is still 0. So that's going to be 0 plus 2x dx dt equals 2y dy dt. Now you could call it x prime and y prime if you wanted, as long as you remember that it's the rate of change with respect to t. So what have we got? We could divide both sides by 2. That 2 isn't really doing anything. And that gives us x times dx dt equals y times dy dt. Okay, now that we've taken the derivative, now we have an equation that relates x, y, and dx dt and dy dt. Now start plugging in numbers. Okay, so it says, up here it says when y equals 5, okay. dy dt, that's the rate of change of y with respect to time. That's what velocity is 5,000 miles per hour. Okay, so the 5 can get put in for the y, and the 5,000 miles per hour can get put in for the dy dt. And this is our unknown rate, the dx dt, but we still need something for x, but we can figure out what x is. Find what x is when y is 5 using Pythagoras. So remember down here it's always 3. So we just have x squared plus 3 squared equals 5 squared, or x squared equals 25 minus 9. X squared equals 16, so x is going to equal 4. It's a distance, so we don't have to worry about the negative solution. So we can take that 4 and plug it in for x. So now we've got values for everything except our unknown rate. So we've got 4 dx dt equals 5 times 5,000. So all you have to do is divide both sides by 4 and solve for that unknown rate, dx dt. So it comes to, it's going to be 6,250 miles per hour. And that's the answer. Because that's what it was asking for. It was asking for how fast is x changing at that moment when y is 5. And dy dt is 5,000 miles per hour. Okay, so any questions about that? So, here's another one. It says, a man 6 feet tall walks with a speed of 8 meters per second away from a street light atop an 18-foot pole. So that 18 feet pole is fixed. How fast is the length of his shadow changing when he was 100 feet from the light pole? Okay, so this is the length of his shadow right here. Oops. We could call that x, say. Now his height is fixed. It's 6 feet. And then I guess we're going to need we're probably going to need this distance too, because it tells us how fast he's walking away from the pole. We could call that y. So in this case, it's not going to be Pythagoras. It's going to be similar triangles. Now they want to know how fast is the length of his shadow changing. So that's our unknown rate. And that's going to be dx dt. Okay, he walks with a speed of 8 feet per second away from the street light. So that's a known rate. dy dt equals 8 feet per second. When he is 100 feet from the pole. So that says when y equals 100. Okay, so we've got similar triangles here. Let me see here. Some colors. Yeah, I'll just bother with that. So there's this little triangle. And then there's a big triangle. Okay, so in the little triangle, we've got that's 6 and that's x. And that's the right angle. And in the big triangle, we've got 18, and I guess what would be this distance be here? Yeah, that would be x plus y. So the ratio of the sides, well, there's several different ways you could do it. We could take x over 6 equals x plus y over 18, right? So that means this over this is the ratio is the same as this one over this one. Okay, or you could have done it other ways. You could have said 18 over 6 is equal to x plus y over 8. X plus y over x. There's lots of ways you could have done it. This way is as good as any. So before we take the derivative, maybe we should just try to simplify it. What you could do is cross multiply. Well, I mean, just multiply both sides by, what you're doing is multiplying both sides by 18, basically. And that's going to give us 18x equals 6 onto x plus y. So 18x equals 6x plus 6y. So that means 12x equals 6y. And we could divide by 6, I guess. And that would give us 2x equals y. So there we've got an expression relating x and y. And then we can take d by dt of both sides, right? So of course this is just going to give you 2 times dx dt equals dy dt. So, and then we can put in our variables. Well, in this case, the x and y are both gone, so we don't need this. So all we need is that dy dt is equaling 8 feet per second. So this is 8 feet per second equals 2 times dx dt. Now we can just divide by 2, and that gives us dx dt equals 4 feet per second. So apparently if he's walking at a constant rate, his shadow is lengthening at a constant rate. So I guess the tip of the shadow would be moving away from the lamppost at a rate of 12 feet per second, because it would be moving, he'd be moving at 8 feet per second, and then the shadow's moving away from him at 4 feet per second. Anyways, that's the rate that the shadow is lengthening. Okay. So the shadow is getting longer. I guess it would be like, when he got farther away, it would be like, sort of like this. And he might be here, and then you have this really long shadow. Anyways. Okay, this is a common, I always use this is a very common problem about a ladder slipping. Oh, here it just gives some steps to solving a related rates problem. Make a sketch if you don't already have one. Define your variables. And variables are things that are changing, and they're all functions of t, time. Set up an equation relating all the variables. Implicitly differentiate both sides of the equation with respect to time, t. Substitute in values for all known quantities and derivatives, but be sure not to do this before step 2 and 3, and then solve for the remaining rate. Okay, so in this case we have a 20-foot ladder leaning against the house. So this is a constant, that's not changing.
It's meters.
Pardon?
It's meters in the problem.
Oh, sorry, okay.
That's okay.
Thank you. Meters. It's a pretty tall house. Oh. Okay, the ladder begins, no, let's see. The bottom of the ladder is prevented from moving by a young child. Suddenly something distracts the child and he releases the ladder. The ladder begins slipping down the wall of the house, picking up speed as it falls. If the top end of the ladder is moving at 1 meter per second when the lower end is 15 meters from the house, how fast is the foot of the ladder moving away from the house at that instant? So we've got two, we're interested in this, x, the distance from the ground up to the top of the ladder, and then there's this distance, y, which is the distance from the house out to the foot of the ladder. And as it slips, of course, x is going to get smaller and y will get bigger, right? So we'll say define x and y as shown. Okay, so of course, what would our equation be that relates them? Yeah, there'd just be Pythagoras again. And this time the constant is on the hypotenuse, so it's just x squared plus y squared equals 20 squared. And so we'll come along, it will go d by dt on both sides. Of course, the length of the ladder isn't changing, so its derivative is 0. And this is going to be 2x dx dt plus 2y dy dt. So 2x dx dt plus 2y dy dt equals 0. Okay, so let's so we've got that constant 20-foot ladder, and it says if the top end of the ladder is moving at 1 meter per second, when the lower end, the lower end is 15 meters from the house, and then we want to know how fast is the foot of the ladder moving away from the house at that instant. So that's our unknown rate. And it's dy dt. And this one here is going to be dx dt is now, because x is getting smaller, we probably want to put that in as minus 1 meter per second. So dx dt equals minus 1 meter per second. Now, if x and y are both getting smaller, then it's not that important if you make them both negative. But if one's getting smaller and one's getting bigger, then your equation won't work unless you do that. Okay, so, and then we've got this other thing, when the lower end is 15 meters from the house. So that's when y equals 15 meters. Okay, so when y is 15 meters. X, we can just use Pythagoras again. 50 squared plus y squared equals 20 squared. So y squared equals 20 squared minus 15 squared. So y is going to be the square root of 20 squared minus 15 squared equals. Let's see. And that comes to about 13.23 meters. Okay, so that's a value we can put in for y. Oh, wait a minute. Did I get x and y mixed up? Oh, shoot. Yeah, you're right. Sorry about that. Yeah, this should have been x. Thanks. Sorry. So all these y's here should have been x. Okay, so you can put that in for x. Maybe I'll just rewrite this down here. 2x, whoops. 2x dx dt plus 2y dy dt equals 0. Okay, so we can put this in for x. And then we have dx dt up here is minus 1 meter per second. And we have y is 15. So we can just plug all those in and then solve for our unknown rate, dy dt. Okay, so 2 times 13.23 meters plus 2 times 15 meters. Whoops, I forgot to multiply by dx dt. Times minus 1 meters per second equals 2 times 15 meters times dy dt. So we can just come along and divide both sides by 2 times 15 meters.
Maybe minus 2 times 15. Because you may use the result.
Oh, sorry. I'm sorry. Gosh, I'm half asleep here. I'll just put that in as a step. 2x dx dt equals minus 2y dy dt. So we'll divide by minus 2. And that just gives us okay, so it's just going to be 13.23 divided by 15 equals 0.8. 8 meters per second equals dy dt. And that's the speed at which the ladder is moving away from the house. Okay, there's worksheets on this on 9. I don't know if I had any with me or not. But I think the related rates problems were on the same worksheets as those, for the most part, as the parametric curves. But when I printed them out, I only printed out the parametric curve problem, so I might want to go back and look at those. So we'll continue with this tomorrow. Got a few more examples.